Hi, this is Seth Newton, and this video is to explain further my poster at Dioxin 2014 in Madrid, Spain, entitled Emerging Flame Retardants, PBDEs, and HBCDs from Indoor to Outdoor Environments in Stockholm, Sweden. Flame retardants are chemicals used in products mostly for indoor use. Levels of flame retardants in indoor environments vary greatly depending on what flame-retarded treated products are contained in that specific environment. However, flame retardants are commonly found in the outdoor environment as well. With these facts in mind, this study sought to compare the concentrations at which flame retardants are found in air and dust in different types of microenvironments, such as offices, homes, schools, or stores. Compare indoor and outgoing air from ventilation systems to what extent indoor environments contaminate the outdoors with flame retardants. And also examine outdoor air and soil for flame retardants in various locations inside and outside of Stockholm to determine background levels and see if the city itself acts as a source of contamination to the outdoor environment. We sought to accomplish these objectives by sampling indoor and ventilation system air using low-volume active samplers fitted with a glass fiber filter and 2 puff plugs. 4 of these sampling trains were connected to one pump to avoid saturation, and the pumps were ran at 12 liters per minute for 24 hours, getting about 17 cubic meters of air. Samples were taken inside homes, offices, schools, and stores. Simultaneously, samples were taken from the ventilation systems near where the air leaves that particular building. Once air sampling was finished, dust samples were taken using a cellulose filter that attaches to an industrial strength vacuum cleaner. Only settled dust from surfaces at least 1 meter above the ground was taken. In apartments, offices, and schools, samples were taken from various places around the room, but to investigate the usage of flame retardants in certain products, dust samples were taken from dust directly on product, and separate samples were taken from areas around those products when we sampled the stores. In all, 4 stores, 4 apartments, 3 offices, and 2 schools were sampled. Outdoor air samples were also taken using a high-volume air sampler fitted with a glass fiber filter and 2 polyurethane foam plugs, similar to the low-volume setup, only on a larger scale. The high-volume samples were taken for 48 hours, collecting approximately 1,000 cubic meters of air. Soil samples were taken from the same location. Grab samples of the top 5 centimeters were taken and sieved to 2 millimeters. The locations of the outdoor sampling sites made a transect of Stockholm from west to east. The analytical method used is published in Analytical Bioanalytical Chemistry by Sellström, and DeWitt. Shortly, low-volume air samples and dust were extracted by sonication in dichloromethane. Outdoor air was extracted by soxhlit in dichloromethane for 24 hours. Soil samples were extracted by rotation in acetone and then hexane. Sulfur was removed using a TBA reagent. All samples were then fractionated on silica columns. 3 fractions were taken as shown in this schematic from the publication method. The elution of several flame retardants was checked, and they were found to come out in fraction 1. Several emerging flame retardants, that is. Fractions 1 and 3 were cleaned up by acid, as shown here, but fraction 2 contained compounds which break down in acids, such as TBB and TBPH, so it was cleaned up further on aminopropyl column. All compounds were analyzed by gas chromatography, negative ion chemical ionization mass spectrometry, except HBCD, which were analyzed by liquid chromatography, tandem mass spectrometry, in order to separate the various isomers. More volatile EBFRs, such as TBECH, pentobromotoluene, and hexabromobenzene, were detected frequently in indoor and ventilation air, while the PBDEs were found more frequently in dust and soil. Other EBFRs of interest include EHTBB, BTBPE, TBPH, and DBDPE. There were no correlations between compounds in indoor air and ventilation system air. However, the concentrations were not significantly different, indicating the variability between specific microenvironments is just as large as the variability between buildings. In dust, the EBFRs that were found so frequently in air were also found, but in very low concentrations, generally less than 10 nanograms per gram, compared to the PBDEs, which often range up to a few hundred nanograms per gram and even up to 2,500 nanograms per gram for BDE 209 in one dust sample. TBPH was the most frequently found EBFR in the dust, ranging from less than 50 and all the way up to 1,500 nanograms per gram. HBCD was found in every dust sample and gave some interesting results in regards to isomer profiles. There was no significant difference in concentrations between HBCD in dust samples taken directly from the products when compared to dust taken near the products, but there was a significant difference in the isomer profiles, namely that there was an enrichment of the alpha isomer in dust that was taken from around the products. This may be due to isomerization, as the other isomers have been shown to become alpha with exposure to light or heat, and alpha is the most stable conformation. Several EBFRs were found in outdoor air, with TBEH being the most predominant isomer. BDE 47 was the most predominant congener of the PBDEs detected. Both EBFRs and PBDEs showed decreasing concentrations with increasing distance from the city of Stockholm, indicating that the city itself is a source of flame retardants to the outdoor environment. Thanks for watching this video. This project was part of the Marie Curie Initial Training Network, InFlame. We'd also like to acknowledge Dimitri Panagopoulos for help with sampling and analytical work, Ian Zamek for his help with analytical work, and we'd like to thank all participants in sampling.